My guest today is Sean Polacik. Sean has 17 years of experience as an instrumentation and electrical technician. He's recently produced a presentation which is called Burdens of the Modern Grid: How Harmonics, Differing Measurement Practices, Poor Device Performance, Lax Calibration Standards, and Residential Load Imbalances Are Driving Inflation from Electrical Overhead. Now, for my followers, my primary problem with so-called smart meters is the synthetic radiation exposures that they impose on everyone in the service area. But today we're going to expand that a little bit. We will be talking about some issues of synthetic radiation exposure, and namely dirty electricity. But we're going to expand our conversation to talk about some of the inner workings of the smart meters, how they create their own dirty electricity, and how the way that they measure power consumption may be affected by that dirty electricity. So, Sean, welcome to the podcast. Thanks for being here. I appreciate it.
I'm glad to be here.
Yeah, let's get into this a little bit. So, help us to understand how the new smart meters maybe are not instruments at all. Maybe they're more like computing devices, and how they differ from what we've used historically, the analog meters with the little spinning disc that I think we're all familiar with. Can you kind of give us an introduction to the difference between those two technologies?
Yeah. Well, you hit the nail right on the head. The new smart meters, as they call them, are in fact not really actually meters. They are computers, and they're multifunction devices that have a multitude of varying functions in them, mostly with the breakdown of just how your data is, your power consumption is being utilized. They do the standard kilowatt hour meters, everybody knows that, but they track time of use as well for specific loads. Like, for instance, the technology is capable of discerning specific appliance waveforms in your house, so they can tell, like, when you turn on a microwave, when you turn on a TV, your hair dryer. They can even look at what channel you're even watching on that television at a certain time. And so they're being used pretty much as just data collection devices as well for consumer behavior. And you can use that any number of ways in marketing, being sold off to third parties. So that's a huge difference from the traditional, like you said, spinny dial meters that we used to have.
I'm sorry for interrupting. There's just a quick question here. Is it true, one of the things I've heard is that you'll be able, for somebody who has a smart meter, the utility, potentially without human intervention, will be able to shut off the power at a customer's home, unlike in the old days with analog meters. They had to at least send out a technician to accomplish that. Is that correct?
Yeah, that is. Because of the way they have the AMI mesh networks now, everything is remote connected over the radio waves. And the smart meters have relay disconnect modules built into them. So they can just pull up your serial number and just say unlatch and turn off your power remotely. They don't have to send anyone out. Which, of course, that poses also a huge security risk for our power grid, because RF open channel communications like that are very susceptible to hacking, for instance, or remote monitoring. Like, say somebody nefarious wants to case your home for breaking in later, they can watch your power usage and see, what time of day you're home, or just, if they just wanted to turn your power off for no reason, in the dead of winter, they could do that. So I find that as quite a bit of a security hole, not just the whole invasion of privacy thing.
Yeah, that's a good point about the susceptibility to hacking. Is that why banks, for example, and maybe other large corporations don't even allow wireless access to their network?
That's exactly the reason.
Okay, so
Because
that
there's so much sensitive data there. I mean, having it open to the public is just stupid.
and I'm sorry for I interrupted there, but yeah, we were going to talk about the old-fashioned meters. They didn't burn down houses. Typically, they had a longer service life. They didn't introduce any kind of dirty electricity. How did those work? And then maybe you could discuss how these new things work from a metering perspective.
Yeah, the old meters, I would say, were very elegant in their design, and that demonstrated by their 40 to 50 years of fairly trouble-free service. To simply put, the spinning little aluminum disc in there. It's conductive, so there were two electromagnets in those analog meters, one for your current, one for your voltage. And when energized, they imparted an eddy current into that aluminum disc, which caused a motive force on that disc, which was proportional to the power you were being used. So that, there's nothing more basic than that for measuring your power. And it was always reliable because you always knew exactly what you're going to get. And they were not susceptible to like dirty power either, because the spinny disc didn't care about dirty electricity or harmonics. It just measured real power.
To understand power, what we're looking at is it's the product of voltage and the current being used. So the older meters looked at both the voltage and the current that was being used, and that was what was recorded by the spinny disc, as you put it, and not really affected at all by these micro transients that you might have in dirty electricity.
Right. The other thing about the old style analog meters was, you mentioned the house fires before with the new smart meters. The patent for the analog meters actually is as a surge arrestor. So they have built-in surge suppression for like a nearby lightning strike. If you never turned over an analog meter, you'll notice there's two metal tabs in the center on either side. And that's exactly what that was for dissipating those high voltage, spikes across the spark gap. So they typically would protect your home from fire damage like that.
Yeah, lightning strike is not dirty electricity, so those two are different phenomenon. But yeah, right. Yeah, I wasn't thinking about the lightning protection. Sorry, go ahead.
Yeah, it's just something else that I find analog meters have over the current smart ones.
So with the new meters, the so-called smart meters, the computer systems, they do things a little bit differently. They're monitoring as well voltage, although some of them are taking a shortcut on that. We'll talk about that shortly. But they're looking at voltage and they're looking at current, but they're not measuring it continuously. They're sampling it. Can you describe a little bit about how that's different from what the analog meters are doing?
And the sensing elements, a lot of the meters, they have what's called a Hall effect sensor, which instead of measuring the voltage and current, it's measuring the flux density of the magnetic field created from the current passing through a wire. So you've got a little semiconductor chip that's next to your wire that is reading that magnetic field strength. But it's not doing that constantly, like you said. The meter is taking like a bunch of sampled points in a given amount of time, and then from those sampled points of instantaneous voltage and current, it is generating an average power use. And that is what it's using to give your kilowatt hour reading.
Let's talk about certification of these meters and how we can know that a particular meter is accurate.
Okay. Well, the current national standard for meter calibration is the ANSI 12.1-2022. And typically when you're testing a meter, your laboratory conditions have to be pure sine wave input power. And it has to be completely free of any any noise, harmonics, any kind of distortion, that's a fairly common practice, for all measurement instrumentation in my field, not just power meters, but so that was pulled in by NIST, because NIST was also part of that spec. So, in light of that, as analog meters, they don't generate any noise in and of themselves. Now, these new meters, because they're computers, they have switching power supplies in them. And of course, for anyone that's listened to your podcast before, and know what you do, those switching power supplies are a horrendous source of dirty power. So as soon as you put one of those meters on the test bench, you've already fouled the conditions of the test, more or less. And if you go into it further too, there's another section in there specifically pertaining to the type and form of meters. This is mainly concerning the difference between Blondel and non-Blondel form factors. So that's a whole other section of the ANSI standard. So the only requirement for total harmonic distortion testing, I guess we would say reliability, only pertains to Blondel compliant meters. And what is on our homes for most everywhere in the world is a 2S non-Blondel meter. So you can kind of see where that is a bit of a problem.
All right. So I want to make sure I understand all of this. So with regard to testing to ensure that these devices are doing a reasonable job of measuring or computing the power usage, the current ANSI standard deals only with the type of meter that's not generally used on homes, and it requires a power quality level, and we talk about dirty electricity as a way of looking at power quality. It requires a pure environment without dirty electricity to test the device. The implication there being that an increase in dirty electricity might change the function of the meter in terms of its accuracy, and the device itself, by its nature, because it has a switch mode power supply, is itself a producer of dirty electricity. So have I got all that right?
Exactly. Wow. And the thing is, the standard itself does list the percentage as being 2% total harmonic distortion. So I did a test here for my own Itron Centron 2 meter, I think is what my utility Duke Energy installed. And actually got talking to one of their metering engineers. First off, I don't know how I convinced them to do this test in the first place. But they sent a tech out, and they pulled their digital meter, and I had an analog meter that we put on, and I had one of those Greenwave broadband EMI meters. And so we took a measurement of the line noise with all of my other breakers turned off and all the other loads disconnected from my house. So it was just reading what was coming in from the street. And so we got that measurement, and we put their smart meter back in, and there was an increase of 4% noise above the noise floor. So as you can see, the standard calls for 2, so that right there already blows the meter out of the water for the standard that it's supposed to be certified for. Found that because the meter because that meter out there that they put on there is a form 2S by the standard, it's not required for testing, so it's a bit of a problem.
Yeah, and to make this all more complicated, not everybody has their own transformer for their home. So if you have 2 or 3 or 4 or more people, your neighbors that are connected to the same transformer, are all of their meters also contributing to the dirty electricity in each other's homes?
Yep. everything on that branch line that's connected will be cumulative. So all your washers and dryers, that are inverter powered, or your heat pumps, all those meters. I mean, you're going to get everybody's noise.
Who gets to say
of course, if
whether
the
a
meter
meter is accurate or not? Are these independent test labs that certify that the meters are accurate, or how does that process work?
Yeah, an independent test lab that meets the criteria for NIST of having traceable instrumentation for conducting those tests can do that. But and this was also listed in the ANSI standard, that any lab that qualifies for that. So, say for instance, by example, First Energy owns Duke Energy, and Duke happens to have a lab that has all the passing criteria to meet that standard. They can do all of their meter certification in-house without having to send it out to a third party.
Yeah, so we've talked about Blondel meters and non-Blondel. Blondel is is it a theorem or a law? Anyway, having to do with electrical engineering and how power measurement can be characterized.
Yeah.
And I believe that you mentioned.
Yeah. So.
Sorry, we've got a little bit of a lag. I apologize. So anyway, there's Blondel and there's non-Blondel meters. And I thought what I heard you say earlier is that the ANSI standard for testing did not apply to non-Blondel meters, which are the 2S or 2 Sierra, and you can read that right on the face of the meter. That does not include the 2S meters. And I know you have a 2S meter, and I went out and verified before our interview. I have a 2S meter at my home as well. So are those excluded from testing entirely, or is there a standard for testing those?
Yeah, it's well, per the NCC 12.1 standard, they're not required to be tested for total harmonic distortion performance at all. Which, just about everybody in their houses has a 2S meter, because they're cheaper for one to buy, because if you go back to Blondel's theorem states, it's a way of ensuring accuracy for load imbalances. So what it states is that you need one less meter element for the amount of wires you have in a service. So for typical residential service, you're going to have 2 hots and a neutral. So that's 3-wire service. So if you wanted to measure that accurately, you would need 2 metering elements to make sure that the voltage on the one hot leg to neutral and the voltage on the other hot leg to neutral is being calculated properly for. Now, if you use a non-Blondel meter in such a situation, you're assuming that the loads between each of those lines to neutral are going to be balanced. It's very rarely an occasion that residential loading is going to be balanced. So that's one area that errors are occurring across the country and the globe everywhere, because people cheap out on metering.
Right. With regard to the Blondel meters, then they're making an assumption that the load is balanced. And that assumption is being made because there are not 2 elements, one looking at the phase A and the other one looking at phase B. It's looking at one of those only, and it's assuming it's the same for the other phase, which really can't be proven. And I wonder if that's a realistic assumption.
It really isn't. It's just, personally, it's laziness in metering is all that is. Or maybe it's, maybe the meter costs like, an extra $60 or something, so they penny pinch and just assume it's going to be an acceptable margin of error and put a non-Blondel compliant meter on the side of a house rather than like a Form 12S, which would be a Blondel compliant and a 5 lug meter base.
Okay, very interesting. So is there any other, part of this metering scheme that we have not talked about so far? We've talked about the testing, the fact that can be done potentially in-house, the Blondel compliant having an ANSI standard and requiring certain testing, and the non-Blondel, which is a 2S, which is what you and I have, don't have that same requirement. The potential inaccuracy being introduced by really only having the ability to observe the voltage at one phase versus both. Is there anything else that we need to know about how this metering works?
Well, I mean, the non-Blondel, as you already pointed out, since it doesn't require the harmonics testing, like I said, there's going to be accuracy problems because of that. There's also one thing for the folks that have gotten opt-out meters that they should also be aware, because these meters are computers. If you ever taken a look at your clock in the bottom right corner of your computer and looked in the time settings, you've probably seen a little tab there called Internet Time before, if you ever made note of that. So what that does is it pulls a time server on the network in order to maintain your clock accuracy. And then the master servers that it pulls is, tied to an atomic clock housed somewhere at the NIST government labs. So the implications are, if you have an AMI opt-out meter that is no longer talking to the network in order to maintain its internal clock, because it uses that clock for its various averaging and time reporting functions, you're going to get drift over time, because electronic components, vary in various tolerances. I mean, you got different resistances, different capacitance, and they're all different from machine to machine because of manufacturing processes. So you're also getting time-induced errors for your opt-out smart meters, which are just going to compound the problem.
I'm going to be sure and put a link to where people can get your presentation, Burdens of the Modern Grid, how harmonics, differing measurement practices, poor device performance, lax calibration standards, and residential load imbalances are driving inflation from electrical overhead. Hopefully, now that I read the full title of that presentation that you put together after our conversation, maybe each of those terms make a lot more sense to people. There is a lot of information here with these so-called meters. They're really nothing like the analog meters that we're used to. The accuracy is potentially really problematic versus a very elegant solution that has served for decades, if not, generations. And then you've got the remote disconnect possibility, potentially without even human intervention, the generation of dirty electricity, and the questions about using the 2S meters in residential
2S
applications, which are not according to the Blondel standard. So thank you for helping us understand all of that. Any last words before we end the interview?
Well, I would say if you could get an analog meter, get that, or protect one that you already got, because they aren't worth the new digitals are not worth anything at all to me. They should never have been installed.
Great words to end on. John, thank you so much for your time today. I appreciate it.
No problem.
The EMF Remedy podcast is a project of EMF Remedy LLC. We'd like to be your trusted guide for achieving a better EMF environment in your home. The contents on this podcast are provided for informational purposes only and are not intended to substitute for the advice provided by your doctor or other healthcare professional. It is not intended to be, nor does it constitute healthcare or medical advice. Opinions of guests on this podcast do not necessarily reflect the opinions of the EMF Remedy podcast.